Okay, this thermodynamic problem has just about everything in it. It's got an adiabatic process, an isothermal process, and a couple of others. Let's take a look at the PV diagram real quickly. We're starting at point 1 in the lower left corner. And we move straight across in an isobaric expansion, that's at constant pressure, to point 2. And what I've done here with these blue lines, I've tried to draw a couple of isotherms in here. So one of those isotherms goes through points 3 and 4. That every place on that blue line is the same temperature. And another one goes through point 2. So those are two isotherms. And then the adiabatic process, you can see it jumps from one isotherm to the other one, from point 2 to point 3. That's an adiabatic process. So we go from point 1 to point 2. That's an expansion. The volume increases. Then we go from point 2 to point 3. That's a compression, and it's done adiabatically. Then from point 3 to point 4, we have a compression that's done in an isothermal way, in an isotherm. And then from 4 back to 1 at constant volume. That's another way of saying that is isochorically. So we end up back where we started after going through these processes, these 4 steps. And the first thing I like to do is make a little table of the points. What's happening at point 1, point 2, point 3, and point 4. So that's the first thing I like to do. And what is the information we should have at each one of these locations? We should have the pressure, the volume, and the temperature. And we are interested in points 1, 2, 3, and 4. So let's take a look at point 1. So the pressure is given, 2.4, 10 to the 5th pascals. And, let's say that's the pressure. The pressure is given, and the temperature is also given. 355 Kelvin. So all we have to do is solve for the volume. This is an ideal gas. So we can use our ideal gas law, PV equals nRT, and so the volume is nRT over the pressure. And let's plug in here. N is 1/4 of a mole, 0.25 moles. R is our universal constant, 8.314 joules per mole Kelvin. Temperature has to be in Kelvin. Pressure in pascals. And that gives us our volume in cubic meters. So I could fill in now my volume, 3.07 times 10 to the negative 3rd. That's in cubic meters. Our temperature was given 355 Kelvin, and the pressure was given 2.4 times 10 to the 5th pascals. Okay. Moving along, point number 2. Let's take a quick look at our diagram. At point number 2, the pressure is the same as at point number 1. And the volume is 4 times as large. That was given. So I'm just going to do that real quickly. 1.23 times 10 to the negative 2. And now we have to solve for because the volume at 2 is 4 times the volume at 1. That was given in the problem. Now all we have to do is solve for the temperature at 2 using PV equals nRT. So the temperature is PV over RT. Pressure in pascals, volume in cubic meters, N is the number of moles, and R 8.314, and that gives us the temperature 1420 Kelvin. So I'll go put that into our table here, 1420 Kelvin. Point 3. Here it starts to get a little tricky. Let's go back and look at our PV diagram. We know a lot of information at point 2. We're trying to figure it out at point 3. And what connects those 2 points? An adiabatic process. So let's go take a look at what we can know about adiabatic processes. We know that PV to the gamma is a constant. And what does that tell us? That tells us that P2 V2 to the gamma has to equal P3 V3 to the gamma. That's the first thing we know. The second thing that we know is that T V to the gamma minus 1 is a constant. And that tells us that T2 V2 to the gamma minus 1 equals T3 V3 to the gamma minus 1. So what is gamma? This is oxygen, and we're told we can treat that as an ideal gas. It's diatomic. So gamma is 1.40. So let's see what we can do here. So we know something about the volumes. We know the volume at 3 is 2 times the volume at 1. 6.14 times 10 to the minus 3 cubic meters. And so the pressure at 3 is going to equal the pressure at 2 times the volume at 2 to the gamma over the volume at 3 to the gamma. And let's just start plugging some things in here. Pressure at 2 is 2.4 times 10 to the 5th pascals. The volume, 1.23 times 10 to the minus 2. Gamma is 1.4, and that's all over 6.14 times 10 to the negative 3rd meters cubed to the 1.4 power. I've got 6.35 times 10 to the 5th pascals for my pressure. And now I can solve for my temperature using the second equation from up above. Temperature at 3 is going to equal the temperature at 2 times the volume at 2 to the gamma minus 1 over the volume at 3 to the gamma minus 1. Let's put some numbers in there. 1420 Kelvin, 1.23 times 10 to the negative 2 to the 0.4 power, all over 6.14 times 10 to the negative third to the 0.4 power. And I end up with 1,875 Kelvin. So I can go punch those back in. And my pressure was 6.35 times 10 to the fifth pascals, and my volume was 6.14 times 10 to the negative third. Okay, one more point. Point number, let's look at our PV diagram. We're going from point 3 to point 4. And what do we know about that path? It's an isotherm, so we can go ahead and plug in our temperature is not going to change. The volume is the same as where we started out, 3.07 times 10 to the minus 3. And now we have to figure out our pressure. Our trusted ideal gas law will come in handy here. The pressure at 4 nRT4 over V4, and we know all of those. 0.25 moles, 8.314 joules per mole Kelvin, 1875 Kelvin over 3.07 times 10 to the minus 3 meters cubed, and I end up with 12.7 times 10 to the fifth pascals.